So welcome back students. Let's move ahead with the chapter. And last time, okay, the previous class, now we have done all the conversions, children. It requires a lot of practice. At this point, what you can do is just give a bit of time to this particular chapter and focus for your upcoming exam, that is for the unit test. So this is your unit test 1. So please focus on your upcoming exams for all the subjects, and once you're done with the unit test, then you can come back and start practicing on this particular chapter. So today also we are going to go ahead with the chapter, and anybody who requires, okay, we are going to plan for this revision tour also for the previous chapter which is there in your unit test. So I will plan something for the revision tour which is a complete theory chapter. Okay, it's a complete theory chapter. Still we will just take a bit of summary of the chapter in form of a revision. Okay, so children, binary to hexadecimal, right? So already we have done binary to hexadecimal. I have taught you the technique, what we are supposed to do, right? Just we have to form, if it is binary to hexadecimal, just we have to form the groups of 4. So that is the same thing that is been told over here in the, that is in front of you. Okay, so let us take the example straight away. So this is a binary number. Okay, that is one, that is okay, one, you can say this is a this is the number basically, and I will just enlarge this, and let me just take the pen, and this is the number. Okay, so what we are going to do, so if it is 1 0, okay, if it is, this is the number, so 1 0 1 0, this is the, isn't this the first group that I'm going to form, right? Let me just take a thinner pen and let me just decrease the size. Okay, so what we're going to do, we are going to form, this is a binary number, and this we have to convert this into hexadecimal. So we have to form the groups, right? So we're going to start from the right hand side as what we have learned. So this is the first group, so from here I can start the first group, right? So this is the first group, that is a group of 4. And why the group of 4 is because we want to convert this number into hexadecimal, and hexadecimal takes 4 bits. And then the next group that we have is this one, that is only 3, we have only 3 bits, right? So this is the first group, that is 0 1 0 1, which stands for what? Which stands for 5, right? And this is 0 0 1, and then I will simply add 1 0 out here. So you can see they have same thing they have done, right? So 0 1 0 0, and it stands for what? That is 4, and that is the answer. Fine, and the answer is over here, that is there written. And then with the decimal points also, how we are going to deal with the decimal point. So this is a binary number, and we want to convert it into hexadecimal. So that is the number. So from point I will take, this is the, after the point, after the decimal point, this is the number, right? They have written this is the point, right? And then we are going to apply the same method for the, for this particular part, that is the right hand side. And you can see what they have done, they have done the group of 4. So 0 0 1 1 from the right hand side, this is the first group, right? That is 0 0 1 1, and then left is only 1. So what they have done, they have added 3 zeros over here, they have prefixed it with 3 zeros. So now, and then this is also 1 0 1 0, right? So 1 0 1 0, this is what? This is 10, that is the binary 10, and 10, if it is 10, so in hexadecimal it will be, that is a symbol A, right? And this is C. Why this is C? Because this is 12, 8 and 4, 12, this is 12, right? And this is 1, so 1 C dot A, and you can see the final answer over here, right? Bring it middle. So 1 C, and then the decimal point A, and 16. So this denotes that this is a hexadecimal number. So I hope this is clear now. So if it is decimal numbers also, a binary decimal convert into hexadecimal, this is the technique. And if we have to convert this into octal, the same technique, only the grouping will be done for 3 bits, right? The same technique we are going to do. So I hope children that this is very much clear now. So hexadecimal to binary also we have done. So this is a hexadecimal number. This is pretty simple. That is, the question will be in this form. That is 10AF. What is F? F is 15, and you can see that is all the bits will be occupied, right? All 1, that is 15, and this is 10, right? This is, so we have taken for F is, that is 4 1, and A is 1010. 0 will be as it is 0, that is a 4 bit, and this is 1. So if we take the answer and then we have to just join them into that answer, right? So this is how we can do it, children. It's pretty simple. Okay, so then we have to convert this hexadecimal number, that is A to F, right? A to F. A is 10, you can see this is the binary 10, right? This is 2, 4 bit 2, that is 0010, and this is what? This is 15, and that's the answer, right? So this is also done, children. And then yes, binary to octal, octal to binary, right? So yeah, let's take this. This is 7428, which means that base 8, which means this is a octal number. We have to convert this into binary. So simple. That is 2010, that is 4, that is 100. So this is a 3 bit, isn't it? Because octal number system requires 3 bits, and that's the answer. So I hope children now this is very much clear that 010 is straight away 2. This is, you can easily guess this now, right? This is 4 and this is 7. All the bits are occupied, so that's the last symbol, that is 7. Then hexadecimal to octal also so simple. And then again, if you have this binary, convert that into octal. What are you going to do? If this is the same number 1 1, you know, 111 this is the number. Then if this is a binary number, convert this into octal. So I have to make a group of 3. This is the first group and this is the second group, and there is 1 0 that I need to add. And then this is what? This is 6, right? And this is what? This is 3, isn't it, children? So this is 6 and this is 3, so that is 36. So that's the octal number system. So same thing. Then hexadecimal to octal and octal to hexadecimal, even this conversion, children, we have done. Okay, so A42, I want to convert this into octal. So we are going to first convert these, find the binaries, right? So 2, you can see this is 2, this is 4, and this is A. And then what we are supposed to do? We are supposed to group this into 3. So you can see this is the first group of 3, that is 010. Second group, you can see 0 0 0. See this is the second group. Then 01, that is 001. Okay, that is 001. This is the third group, and 101. This is the fourth group, and this is the answer. Why? Because we wanted to convert hexadecimal to octal. So if it was octal, so I have to make a group of 3, and so we have this answer. So hexadecimal to octal or octal to hexadecimal. Remember that first conversion that will take place will be binary. First convert that into binary, form the groups, and then write the answer. It's pretty simple, children. And then you can see octal to hexadecimal also they have taken. So obviously 2, that is octal number, right into the binary with a bit of 3, group of 3, right? That is how, see, this was, we took into binary, hexadecimal into binary, but with a group of 4, because that's a hexadecimal number. So, and then we converted the group of 3. But over here, this is octal. So first I will take the group of 3 using the 3-bit representation, and then convert this into 4-bit. So you can see 0010, 0010, then 0111, right? This is the second, and left is only 1, children. So I'm adding 3 zeros over here, and that is the answer, right? So this is also done, children. So I hope this is very much clear now. And then this is the table, children. Already I have shown you this table, what this table is exactly. Okay, already we have done this. Right. So this is all about this is all about the convergence children. And then what is left in this particular chapter is binary representation of integers. Okay, that is positive and negatives. Okay, this is what we have to learn. Now what is happening in the digital computer is, if representing integer numbers means whole numbers, and we are going to first understand about the whole numbers only. But this is the chapter about for the integers itself. So everything is in the stream bytes, basically 0 and 1. So if it is 5, so it is going to be 0 0 1 0 1, isn't it? But if it is minus 5, so minus 5, how I am going to represent, how I am going to show minus 5? And there are certain three techniques that we have. Okay, and that is the techniques that we are going to understand. So let us understand the techniques, children. I will read out this for you. So binary numbers can be represented only by 0 and 1. Okay, I'll take a highlighter. But cannot use the sign, which sign? That is a minus, to denote the negative numbers, or positive to denote the positive number. And that's the problem. But then in computers, for every problem we have the solution. So it must be either 0 or 1. So we are supposed to use a 0 and 1. It has to be 0 and 1. So everything is in 0 and 1 only, and using that bit 0 and 1 we can actually solve the problem. Please understand this. So there are three methods to represent binary numbers, that is the negative numbers basically. Okay, for negative numbers, the first technique is sine and magnitude method, second is ones complement, and third is twos complement. So these are three methods that are used in computer science, and we are going to learn all the three methods. The first is sine and magnitude method. Okay, so sine and magnitude method, children, in this method the technique that is used is the first bit is considered as a sine bit. Okay, the first bit from the left hand side, okay, will be considered as the sine bit. Here the positive number starts with 0. So if that first bit is 0, if the first bit is reserved for denoting the sign, basically the first bit is reserved for denoting the sign. So if it is 0, so it is going to indicate that the number is positive. And if the number starts with 1, so it indicates that the number is negative. Okay, let's take an example. So this is 25 and this is a decimal number, and they have converted this number into binary. Since this is a positive number, okay, now this is a complete 25 is a positive number. So 11001, right? And we want to, this is a binary representation, and we are going to represent this number into 8-bit, that is 1 byte. Okay, word of 1 byte. So 1 byte is equal to 8 bits. Fine, 1 byte is equal to 8 bits. So the first thing that is done over here is this particular number is represented in form of 8-bit number. And how to do that? Just add zeros. Just prefix this number with zeros. So we can see there's the same number 11001. So 1 2 3 4 5. So these are 5, and I've added 3 more. So this becomes 1 byte. Okay, what technique did I use? I have prefixed these numbers with 3 zeros. So this is now completely 8 bits, and so this is 1 byte, isn't it, children? 1 byte. Suppose if the number is minus 25, okay, if it is 25, then it will be represented as this. So simple. What difference do you find between these two numbers? This was a positive number, and if you really focus on the first bit, that is the 0 over here, right? That is 0. So this number is starting with 0 means this particular number is a positive number. That is 25 is a positive number. And the same number, if it starts with 1, okay, so that 1 bit is reserved bit, understand it, then it is considered that this particular number is a negative number. Okay, it is a negative number. So 0 will represent as a positive number and 1 will represent as a negative number, and that's the technique, and the technique that is called as sine and magnitude method. Okay, so that's the first technique. It's pretty simple to understand. Okay, so that was the first technique. And now we will go for understanding the ones complement method. Even this is actually pretty simple. Ones complement is very straightforward, and what they exactly do in this is, if it is a negative number, if it is a positive number, the number will be kept as it is. If it is a negative number, then we are going to convert every 0 to 1 and 1 to 0, and that is so simple technique that we have. So let me just read out the theory. In this particular method, the positive number is represented as same as the binary number. If the number is negative, right? If the number is negative, what we are going to do? Then we need to find the ones complement of the binary number, and that is the technique that we are going to use. The ones complement of binary number will replace every 0 with 1 and vice versa, which means 0 to 1 and 1 to 0. Let us take an example. So definitely they might have given some example. Number is 86. So if it is 86, I convert this number into the binary using the technique, right? Divided by 2, and then this is a bottom to up approach, and that is the number. So this will be represented as it is, and then you can see the answer over here. The answer that they have written is into 1 byte, that is 8 bit. So what we need to do, children, just add zeros. So this was like, how many bits were there? 1 2 3 4 5 6 and 7 bits. So only 1 0 they added, that they have prefixed this number with 1 0. So that is a 8-bit representation, that is 1 byte they have represented. Okay, but if it is minus 55, then what we are going to do, children, that is, this is the number, bottom up approach, and that's the number. So this is 1 2 3 4 5 6. So there are 6 bits. So how many zeros I have to prefix? That is 2 zeros. So you can see this is the 8-bit representation of the number. Right, now we have represented this number as 8-bit, and the next step that we need to do is, this is a negative number, so we will convert every 0 to 1 and 1 to 0. So what we're going to do, so this is first, or we can start from any side, that is from right hand side or from the left hand side. It is not going to make any difference. So 0, first is 0, so I'll convert that into 1. Second is also 0, convert that into 1. Now the third bit is 1, so I'll take that as 0. Fourth is also, this one will also become 0. Now again comes 0, so I'll take that as 1. And then there are 3 1s, so I'll take that as 3 0. Simple as that. And that's the answer that I'm going to have. And you can see that's the answer that they have done over here. Okay, so that is ones complement. So this is the ones complement final answer, and this is 8-bit representation. Okay, that is a 1 byte representation. Okay, so I hope this is very simple and straightforward, children, right? Every 0 has been converted into 1, and 1 has got converted into 0. So this is how we can represent the negative numbers in computer science. So this is second technique. Okay, so let's wrap it up with the 2's complement. Okay, that's the last thing that we're going to take today, that is 2's complement number. Even 2's complement method, okay, let me just read out. So in this particular method, the positive number is represented as a binary number. So if it is a positive number, we are not going to do anything. In all the 3 techniques, we don't do anything. Okay, if the number is negative, and then we are going to apply the technique. If the number is negative, then either the magnitude method or the ones complement or the 2's complement. Then we need to calculate the 2's complement as of the binary number. How we are going to do this? Let us take an example, that is 87. So if it is 87, so that number got converted into the binary number, to bottom to top approach, and this is the number. How many bits are this? That is 1 2 3 4 5 6 and 7. So I need to add 1 0 over here, isn't it? So you can see that's the 8 bits, that is 1 byte representation. First thing that we need to do, children, computer works in form of bytes, understand it? So we are going to take that number in form of 1 byte, so that is 8-bit representation. any number you can just form in a form of 8 bytes, and it won't make any difference to that number. It is just that it is 1 byte. Understand it. So the first thing that we need to do is represent that number into 1 byte. Okay, so this is a positive number. So as I said, positive number, we're not going to do anything with the positive numbers, comes with the negative number, and then this is a bottom to up approach, and this is the number. So these are like 6 bits over here, right? If it is 6-bit, how many zeros I'm going to prefix that? That is 2 zeros. This becomes what? 1 byte, isn't it? This becomes 1 byte. Then what I'm going to do now, I'm going to convert this number into 2's complement, and for converting that number into 2's complement, the first thing that I need to do is convert this number into 1's complement. And how I'm going to convert this number into 1's complement is, see, let us understand 0 0. So I'm going to write 1 1, right? That's 1 complement, then 1 1. So I'll convert that into 0 and 0. Then comes 0, that is 1, then 0 0 1. Isn't this the 1's complement? And you can see the answer over here, right? 1 1 0 0 1 0 0 1. So the first technique is, to take the 1's complement, and then the next technique, to convert this into 2's complement, just add 1 to it. Okay, we have to add 1 to it. Now how are we going to do this? How we're going to add the binary numbers? These are all binary numbers. So basically 1 plus 1, normally 1 plus 1 is what? 2, isn't it? So if you take binary, that is 0, sorry, that is 1 0, isn't it? That is 1 0, right? 1 0, that is 2. So what we're going to do with this 1 0, we're going to take that as carry 1 and that 0 as over here. Fine. 1 1 is 2, so that is 1 0, that's the binary number, and you don't have to form this into a 8-bit and all. Okay, just 1 0 you have to take. Okay, so 1 0, and then there is 0, so there's only 1 that I carried, so it will come as it is, and then rest of the numbers will be as it is. So this is 2-bit 2's complement, I'm going to say. Okay, so they have shown, definitely they might have shown this. Okay, so you can see that what they have done is, first they have converted, see, this is a number which is converted in what? This they have converted the number, this was the original number. First technique is convert this into 1's complement, so this was the result of it. Then they have added plus 1 over here, and then they are saying 1 plus 1 is equal to 2. The binary what they have shown over here is 1 1, that is wrong, that is 1 0. That is a mistake, children. Okay, that is 1 0, and you can see they have taken 1 0 over here. So see, they have carried 1 and they have taken 0 over here. Okay, so 1 0, and then the 1 will come as it is and the rest of the number, and this is called as, this is the 2's complement. That's it. Okay, okay, just minus 54, right? So that was the negative number, and so we have to convert that into 2's complement. So the final answer, you can see that written is over here, right? So minus 52 in 2's complement will be this. Okay, this is also very simple, nothing really complicated about it. If it is 2's complement, first technique is first step is to convert the number into 8-bit, that is 1-byte representation you have to do. Second step is convert that number into 1's complement. And how we are going to convert the number in 1's complement? If it is 1, make it as 0. If it is 0, make it as 1. That is pretty straightforward. And then we are going to add 1 to it. If this would have been 0, okay, 0 plus 1. So 0 plus 1 is what? 1. So that is going to be anyway 0 1, right? Only 1. So we are not going to, if this is 0 and 1, take 1 straight away, right? 0 1 is 1, so you will straight away you can write 1, but here it is 1 1, so that is 2. So carry 1, take 0 down. Why? Because 2 is this 1 0. So even they have done this for the bottom up approach. Minus 77, the same technique, children. See, this is 1's complement. You can see ones complement first, 8-bit representation first, that is 1 byte, then convert that into ones complement, and then you can see that is the number, and plus 1. Now this is 0 and 1, so 0 plus 1 is 1, this is 1 as it is 1, and the rest of the number will be same, and that is the final answer over here, right? So this is the technique, children, and pretty straightforward and simple. So children, I'm not giving you any work at this point because for your upcoming exam, so you have time out of the exam, then please you can spend some time and practice it, otherwise just focus for your upcoming exam, and then once the exam gets over, then I will give the exercise part, so that will be good for you. So I don't want to put any burden on you at this point. Okay, let the exam get over, then I will give you the exercise part, you can complete that. What is left in this chapter is how to represent character, the ASCII characters, and it is very simple and straightforward, and with that we are going to end the chapter. Okay, almost all it is over, children. So that's it, children, for today, and then please focus on your upcoming exams. There is only one chapter, that is software concept. Again and again I'm repeating it so that there is no confusion to anybody. Okay, so bye for now.